Sorry for not being here today. Son was thrown up last night and woke up with a fever, so this might feel a little rushed. I came in early, so I need to get these done and then get back home and stay home with him. But hopefully the gist of this lesson, at least the point, comes across. So we've talked about this idea of indefinite integrals. That's what we've been doing so far. And an indefinite integral, if you remember, if I would integrate x squared plus 1 with respect to x, well, we would get 1/3 x cubed plus x plus c. And what we're finding when we do an indefinite integral is the antiderivative. We're finding basically infinitely many functions that we could derive that would get us back to where we started. That's what an indefinite integral is. It finds you a family of graphs, if you will. Well, there's also this notion of definite integrals, which I kind of got into when I showed that computer program last time, where it filled in all the rectangles and it calculated an area. Well, a definite integral is different than this. So there's two different types of integration. They go hand in hand somewhat, as you'll see, not this lesson, but probably next time. So let's kind of talk about the difference. So I'm going to skip some of this stuff. In my Black Day class, I got into the math behind the definite integral. I don't think it's going to show up on your AP exams, but I did think that it was worthwhile talking about, at least while I was there. I don't think it'd be worth getting into all that with me not being there and just doing a lesson video. So I'm just going to dive into what it is and what it looks like. So a definite integral is still the integral sign, except now we're going to have numbers above and below the integral sign. And these are called our limits of integration. This would be the lower limit of integration. That would be the upper limit of integration. And essentially, this is our interval that we want to calculate the area under a curve. And we would say we want that area from 1 to 3. We only want, if we had, let's say, some graph, and it looked like this right here, and we want the area under that curve, but we only want it from 1 to 3. So we're only focusing on this region right here. That's what these limits stand for. Okay, exactly where do we want that area calculated? And then you'll have some function inside of here, just like normal. Here's a definite integral. So it looks just like this. The only difference is now we have lower limit and upper limit. This is calculating the exact area under a curve. Okay, so a definite integral like this is a number. Okay, it's a number. And that number, as I showed last time on that program, it could be positive, it could be negative, it could be 0. Remember, if it's below the x-axis, our area turns out to be negative. And an indefinite integral, like I just showed right here, so an indefinite integral, like this, so it's the same thing, just without the limits, represents the antiderivative. And that's when we would have to put the plus c on the end. And essentially, we're finding all the graphs, or all the functions, that we could derive to get back to x squared plus 1. So a definite integral is a number. An indefinite integral is a family of graphs, a function. Okay. Today's lesson is not going to be about how we calculate these by hand. We're going to learn next class how we actually do this and find this area by hand, algebraically. But today's lesson is just about what does this mean graphically. So we're just going to talk about what is a definite integral even referring to. Okay? So it says, sketch the region whose area is given by the definite integral, then use a geometric formula to evaluate the integral. Since definite integrals are all about area, oftentimes we're going to have to use geometric formulas that you know from geometry. Like you're going to have to know how to find the area of a triangle, a rectangle, a square, a circle. All those 2D shapes that showed up all the time, we're going to have to know how to calculate those areas. They show up a decent amount of times on the AP exam. They'll give you a graph, and they'll call it G, and they won't tell you what the function of G is, but the graph will contain geometric shapes like triangles and circles and semicircles and things like that, and you have to use your knowledge of those area formulas. So it does show up a decent amount. So let's talk about what this is. Well, this function right here is really just a y equals function. This is like saying y equals 4 minus 2x. This is the graph that we want to graph on our coordinate plane. So I'm going to first graph the line y equals 4 minus 2x. So the y-intercept is 4. And then the slope is negative 2. So we're going to go down 2, right 1, down 2, right 1. We're going to draw that line. Now, here's what's important to point out. When we do definite integration, we're going to have boundary lines. Like this is referring to a specific region in the coordinate plane. Let me explain what your boundary lines are and how you know what they are. One of your boundary lines is always going to be whatever this function is. So this thing here is like one of your boundary lines. Another boundary line that it's not explicitly stated is the x-axis. When we are integrating with respect to x, then the x-axis is one of our boundary lines. So basically we're bounded by this x-axis, this graph, and then our limits of integration, if we're integrating with respect to x, these are x values. So we're integrating from 0 to 2, here and here. And these are essentially x lines. These are like, you could think of them, and this is probably the only time you'll think of them this way, but you could think of these as two vertical lines, like x equals 0 and x equals 2. And these, again, are like boundary lines. So our region, let's think about what we're bounded by. The x-axis, this graph, this vertical line, and this vertical line. So if all these are boundary lines, well, then we're bounded in this little triangle right here. So this definite integral is just referring to the area of this triangle right here. That's what this whole thing is standing for. And so we know how to calculate the area of a triangle. It's 1/2 base times height. Our base is 2. Our height is 4. So 1/2 times 2 times 4 is 4. So this definite integral right here would equal 4. That's just the area of that triangle. But again, we'll learn analytically or algebraically how we go about doing this without graphing next class. So this one here says we're going to find the area from 3 to 8 of 6 dx. Well, this is just like the line y equals 6. That's what this is standing for. You can even write that out if you would want. Like this is y equals 4 minus 2x. This is y equals 6. So that is a horizontal line crossing the y-axis at 6. Y equals 6 would be right here. So we're bounded by the x-axis, that line, and then these two vertical lines right here. So 3 and 8. And you don't need to draw these vertical lines. I'm just trying to emphasize that as being boundaries. And so we're in this little rectangle right here. So area of a rectangle is length times width. So 1, 2, 3, 4, 5, and then 6. 5 times 6 is 30. All right, so things get a little more interesting. You can get a little more involved. So it says, sketch the region whose area is given by the definite integral, but you do not have to calculate the area. Okay, so this one's a little messy because unless you know what y equals square root of r squared minus x squared looks like, it'd be kind of difficult to graph. And so I just asked my Black Day classes what they thought this looked like. And maybe you might want to think about what this looks like as well. It's good to think. But this is going to be the top half of a circle. It's a semicircle. And I'll explain how I know that. So we look at this, and I'm going to try to manipulate this to get it into a form that you guys are more familiar with. So I just want you to watch this. So if I square both sides, I get y squared equals r squared minus x squared. And then if I add x squared over to the left, I get x squared plus y squared equals r squared. And this is your circle formula right here. This is your generic circle formula centered at 0, 0 with radius r that you should have learned. Well, I know you learned in Algebra 2. You hopefully learned it in geometry as well. But that's a circle. And this is only standing for the top half of the circle because this right here is a positive square root. No matter what I plug into these values, this will always become a positive value. So it's this graph right here. It has a radius of r, centered at 0, 0. We know the center's at 0, 0 because there's no numbers here. So our center's at 0, 0, and it's just the top half of that semicircle. And we are integrating from the left radius to the right radius. So our area would be right here. And it says you don't need to calculate it because we don't know what the radius is. All right, the next one's even more interesting. So I talked about up here how if you integrate with respect to x, then this is like y equals 4 minus 2x, and this is like x equals 0 and x equals 2. Well, if you integrate with respect to y, everything flips. Okay, everything flips. So these are now horizontal lines, which we'll look at graphically, and this is the equation x equals y minus 2 squared. And now we need to think about how we graph x equals y minus 2 squared. Well, think about what the x equals y squared graph looks like. X equals y squared is a sideways parabola, opening to the right because a is positive. Well, this right here is really similar, but here's the generic sideways parabola formula. There's a reason why we teach you guys all this stuff in Algebra 2. It's not just so it goes away. It's so that we have some understanding. So here's the generic sideways parabola formula. Right here. Where h comma k is the vertex. So right here, our h is 0, our k is 2. So our vertex of this would be at 0, 2. And we know the parabola is going to go something like this. Okay, that's what we know for sure. Now, a couple of things. When we integrate with respect to y, we're now bounded by the y-axis. So before we were bounded by the x-axis, well, now we're bounded by the y-axis. That's one of our boundary lines. We're also bounded by these horizontal lines. So now 0 and 2 are not x values, but now they're y values. So our other horizontal boundary lines are 0 and 2. And we're also bounded by the graph, this right here. It would be pretty helpful to know where this is crossing the x-axis. And so think about how you can find x-intercepts, ever. To find x-intercepts, put 0 in for y. So negative 2 squared is 4. So I know this is crossing the x-axis at 4. And so our region, we're bounded by this horizontal line, the y-axis, and this curve. So our region is right here. Now again, we don't have any formulas to find this area. That's why it says you do not have to calculate this area. But like I said, next class we'll learn how to do this by hand. We'll actually be able to find the exact area of that curve right there. The next one just goes the other direction. It says set up the definite integral. Now I know we're going to be doing it with respect to x because if you look, our entire thing is touching the x-axis. So I know that now this is going to be more of an x type of problem. See where it's hitting the x-axis the entire time, x-axis the entire time, and then same thing here. So we're integrating. Our limits are going to be x values now, so 0 to 4. And our function, or our curve, if you will, is this line. So the equation of this line right here is what's going to be our integrand, the thing inside of the integral. So the equation of this line, well, the y-intercept is 0. The slope is 2 over 4, so 1/2. So 1/2 x is the equation of that line. And then we always have to put the dx here on the end. We always have to put what this is right here anytime we set up an integral. One thing on the AP exam, you'll have to write a lot of integrals on free response questions. So many students forget this because they know how to find the limits. They'll put the function here and then forget this. So we've got to put that. And there's our definite integral right there. All right. As with anything, there are properties of integrals. So I'm going to put these up. You guys can pause this. I'm gonna just show this and kind of talk through them. Then you can pause it and write them down. That way, I don't need to keep this video running too long. So you guys can pause this if you want now and jot these down, and then unpause it, and I'll kind of talk through each one a little bit. So go ahead and pause it and jot these down. Okay, so just some real quick explanations of these. This first one's kind of a no-brainer. If your lower limit and upper limit are the same, So like if you're integrating, if your span is from A to A, then there is no area. You just have a vertical line, so your area would be 0. So it's kind of a no-brainer. This doesn't really show up very much. The next one is really important to understand. We really need to focus on this one. So normal integration, our limits will go, are from least to greatest, typically. We'll be integrating from left to right. Like we'll integrate from A to B, typically. However, a problem could be set up in such a way where it flips those two numbers, where it puts the bigger one on bottom and the smaller one on top. When that happens, all it does, it changes the sign of your answer, of your normal answer. And what I mean by that is this. So let's say, I talked last class about how if we have area above the x-axis, like this, then the integral is positive. However, if you would integrate from B to A, you'll actually get a negative answer when you integrate. So if you integrate from right to left of something that's above the x-axis, you're going to get a negative answer. Where this gets tricky is when you have something below the x-axis. So let's say you have area like this, from 0 to 4. And I say find this integral and integrate from 4 to 0. Well, typically this is going to give you a negative answer, a negative area. But if you're integrating something below the x-axis from right to left, our answer is actually going to turn out to be a positive value. That's when it'll get kind of tricky. So typically things below the x-axis, the integral is negative. But if you integrate from right to left, it flips the sign there. So negative, negative gives you a positive. You'll get some practice with that on your assignment, I'm sure. This next one I kind of associate with the segment addition postulate from geometry. Remember, the segment addition postulate says if you add these two small lengths together, you get the big length. So it's pretty intuitive, and that's what this is saying here. If you would integrate, like if you split the region up and you integrate from A to C, and you add that to the area from C to B, well, you'll just get whatever the integral is from A to B. That's what this integral is saying right here. This next one's really nice, and it has showed up a couple of times already with derivatives and limits. But if you have a constant being multiplied to a function, you can actually pull that constant out in front of the integral. And this turns out to be really nice because when we do these definite integrals by hand next time, it can get kind of messy. And so anything you could pull out in front and save for the end does turn out to be a real big time saver and just saves a big headache. So a nice little property. And the next one just says if you're integrating the sum or difference of functions, then you can just split it up into two functions that are being added or subtracted and just calculate each one separately. It only works with addition or subtraction though. There is no product rule and there is no quotient rule for integrating. We'll get into other techniques and how we deal with those, but not today. So go ahead and try the very last 4 problems. Pause it again. Try the very last 4. It'll take you a couple minutes, and then I'll put the answers up. Okay. Here are your answers. If you got them, you can turn off the video, and you can start your assignment. If not, you might want to take a look at what happened here. So, all right. Again, you guys have your assignment. I wish you luck. If you have any questions, shoot me an email. I'll be at home being pretty bored. So if there's something that comes up you guys need help with, let me know. See you.